Well, welcome to our video series. We're starting here with quantitative methods, basic concepts, part of two study sessions that make up quantitative methods, which is 12% of the level 1 exam. So the first reading we address here is the time value of money. So let's just jump right into that with our first learning outcome statement that has to do with interpreting interest rates. So what do we have here? Equilibrium interest rates are the required rate of return for a particular investment. And they're also referred to as discount rates. You'll see as we move forward through this reading that when we talk about interest going forward, we talk about compound interest because it builds on itself. When we're taking a future value and getting the equivalent present value and we're dividing by 1 plus the interest rate, we'll refer to that as discounting. And also we can view interest rates as the opportunity cost of current consumption. Because if you don't consume today, you're able to consume more tomorrow because of positive interest rates. So that's the trade-off between current and future consumption. And so that's the opportunity cost or the price of consuming now rather than saving, earning interest, and consuming later. Now, we can think of interest rates as being kind of a build-up, and we'll see this throughout the curriculum. We start with the real risk-free rate. Now, it's real because inflation is taken out. Whenever we say real, we're talking about purchasing power, how much stuff you can get, not how many dollars or euros or yen you have. But once we add a premium to that for expected inflation, we have the nominal risk-free rate here. And so the nominal risk-free rate includes that inflation, but it's still risk-free, default risk-free. Now, for other securities or loans that have risk to them, we'll add a default risk premium. Liquidity, the ability to readily sell a security, a loan, for its intrinsic value, varies across securities, and some are less liquid. And if they're less liquid, then there'll be a premium for this lack of liquidity too. So that's our liquidity risk premium right here. And the third premium we've got in here is a maturity risk premium. You can think about this especially with bonds. The longer the time to maturity, the more you've locked in a given rate for a period of time. And most often in the market, there's a maturity risk premium for that. Higher yields, higher interest rates with longer-term securities. Now, our next LOS here, and you'll see on these up in the left-hand corner, we've got calculate and interpret. Those are the command words from the learning outcome statements, just to keep us on track with these and what we have to get out of them. So this is clearly a calculate learning outcome statement here. And our point here is that if we had a stated annual rate of 12% and compounding was annual, then that's what we'd earn. That would be our effective return. Our effective annual return would be 12%. But if we say the stated annual rate is 12%, but compounding is semi-annual, twice a year, and that's why we've got m equals 2 over here, the number of compounding periods, then we just divide that stated rate by 2. And what we're going to earn is 6% compounded every 6 months or twice a year. So in that case, the mathematics of it is we take 1.06 and we square it. We multiply it times itself and then subtract 1 to get our effective annual rate, the EAR. And that effective annual rate, 12.36. Now, the next thing I want you to notice is as we increase the number of compounding periods, we increase the effective annual return. So with quarterly compounding, we divide 12 by 4 and get an effective quarterly rate of 3%. And then we compound that for 4 quarters, just the same way we did with the semi-annual compounding, except now we have 4 periods, and we get a little higher effective annual rate, 12.55%. And our last example here with monthly compounding, we're earning 1% a month. We compound that over 12 months, and we see the effective annual rate is 12.68%. So that's like with your credit card bill. If it says your annual rate, your stated annual rate is 12%, and yet they bill monthly with a 1% rate, and on outstanding balances, compound that each month, so over 12 months, an outstanding balance would accrue an interest expense of 12.68%. Let's do an example of the effective annual rate here. If we've got a $100,000 CD, that's a bank certificate of deposit, and it has a stated annual rate of 3.6% that pays interest quarterly. Well, we need to figure out the effective annual return or effective annual rate on this. So we divide that by 4. There it is right there. So we've got 0.9% each quarter, 1.009. There we've added the decimal equivalent of 0.9% to 1. And we square it twice or take it to the 4th power minus 1. And we see the effective annual rate on that is 3.649%. So what if compounding were monthly? Straight ahead, divide it by 12, get 0.03, compound that for 12 periods. So we take 1.003 to the 12th power, subtract 1, and get 3.66%. Again, the effective annual rate is higher for more frequent compounding periods for any given stated annual rate. Now the next thing we want to look at here for LOS E is the present value of a perpetuity. Now perpetuity is a series of payments that goes on forever. And sometimes we think about preferred stocks as being perpetuities because they don't have any maturity date. They pay a specified dividend forever, essentially, is the contract. So here we have a preferred stock that will pay 8% a year forever. And our required rate of return here, our discount rate, is 10%. What is the present value? Well, clearly we can't use our regular tools here and take the present value of an infinite number of terms. So we have to rely on our calculus of convergent series. But since some of you may not remember that all that clearly from your classes, we can look at it another way as well. Because if we're going to take 8% a year out of this forever, we better be just taking the interest. We can't take any of the principal or eventually it would go away. So we could set this up and say, well, we need 8 per year. The rate of return, so $8 a year equals 10% of, let's call it X, some value. So how much would I have to put in an account that paid 10% a year in order to get $8 a year in interest forever? Well, we could just rearrange that and put A, divide it by 10%, 0.1, and that equals X. So if we put $80 in the bank at 10%, we'd earn $8 in interest per year, and we could draw that out forever. So that's another way to look at this. And we'll advance the slide and see that this is what leads us. We've got this perpetuity that goes on forever. We're taking the present value of each one, but what that comes down to is this formula that says that the present value of that is just the payment over the interest rate, just as we had before, and we get a present value of this perpetuity of 80. So remember that. The payment divided by the appropriate discount rate or interest rate is the value, the present value of a perpetuity, an infinite series of equal payments. Next, we need to take a look at the future value of a single sum. The mathematics of this are pretty straightforward. If we have $200 today and we earn 10%, and now we're thinking an effective rate of 10%, per year for 2 years, how much will we have? Well, we're looking at the calculator solution, but let me put the mathematics of it up here as well. We start with 200, we multiply it by 1 plus the interest rate, so that's what we have at the end of the first year. 200 times 1.1, that's got to be $220 at the end of the first year. But the second year, we earn interest on that full $220, the original principal of 200 plus the interest. So we're earning compound interest, interest on interest here. And we can just rewrite that, 200, the original value, times 1.1 squared, 10% compounded annually for 2 years, and see that the future value is $242. So what we're saying here is that an interest at 10%, $200 at time 0, and that's going to be our notation here. T is always how much time has passed from right now. So that's T equals 0, time 1. This is T equals 1. This is 1 year later. And T equals 2 is 2 years later. So the calculator solution there on your time value of money keys, 2 periods, 10% interest rate per period. Our present value is 200. We're not making any more payments into this account. We're just letting it earn interest, and calculate our future value, and we get minus 242. There's 2 permitted calculators for the CFA exam, the HP12C and the Texas Instruments, or TI Business Analyst 2, the BA2. That's this one here. If you're not familiar with the HP12C, please get and learn how to use the TI calculator. And when we talk about the time value of money, we've got 5 keys to deal with. Number of periods, the interest rate, the present value, the payment, and the future value. And if you're not familiar with that, please check out one of our videos in the resource library. We've got one that says something like how to run your calculator, and you'll find that very useful. So we have the calculator solution here. Put in those, compute present value, and we get minus 242. And that minus sign just means if we put the money in the bank, we get to take it out at the end. If we borrowed it and we had to pay it back in 2 years, then that'd be money to us now and money out later. That's why the difference in signs there. So this is just going backwards here. If we have a $200 that's going to be paid 2 years from now, what's the present value? Well, now we're just putting that as the future value. We're putting as minus 200 and solving for the present value. And the mathematics of it is instead of multiplying by 1 times the interest rate, we're dividing by it. So instead of moving forward in time in terms of value, we're moving backwards in time to the present. So since it's 2 periods, we divide by 1 plus the interest rate squared and find out that if we put $165.29 in the bank today at 10% compounded annually, at the end of 2 years, the value would be 200. Now we want to talk about annuities, series of equal payments. So we've got a simple annuity here. We call it an ordinary annuity because it starts 1 period after today. So the first payment goes in 1 year from today, second one 2 years from today, third one 3 years from today. So all we're going to do is use our calculator to take the present value of all 3 of those payments. We could just as easily, well, I don't know if it's as easy, but we could just as correctly take the present value of that $200 at time 1, the present value of $200 at time 2, and the present value of that third $200 payment. Add all those together, and that would be the present value of this annuity. Now take note of this big red arrow here. If I use the right end of my pen here, we've got this big red arrow. And that's because when your calculator is in end mode and you do a present value calculation, this is what you're going to get. You're going to get the present value 1 period before the first annuity payment. And as I said, we refer to this as an ordinary annuity. So let's just take a look at the calculator strokes and the mathematics of it. So here's the way I just suggested we could do it. Take the present value of each of the 3 payments, add them all up, and get $497.37. How would we interpret that? Well, we can interpret that to say if we put into an account $497.37 now, and that account pays an annual effective rate of 10%, we could withdraw from that account $200 1 year from now, $200 2 years from now, and $200 3 years from now, and that would be the last penny in the account. It would be completely exhausted. And now we see the calculator solution below that. We've got 3 periods. Our interest rate is 10%. Our payment we've put in as minus 200. Our future value is 0. This account will be exhausted with that third annuity payment, and compute the present value. And what we get is, don't forget, this red arrow. And you'll see as we get to begin mode rather than end mode on the calculator, that's when that arrow is going to be in a different position relative to our annuity. But here we're still staying in end value on this calculation here, and now we're just moving forward in time. And you can think of this question as being, well, what if I had an account and I put 3 deposits into it? One 1 year from now, one 2 years from now, and one 3 years from now. And it earned interest at the rate of 10% per year. Well, we can see that that first payment is going to earn interest for 2 years. And so it will turn into this at time 3. See, there's our big red arrow. So now with our calculator in end mode, and we solve for future value, it's going to give us the value at time 3 on the day of that last deposit. So this second $200 deposit earns, 10% for 1 year, and that last $200 doesn't accrue any interest on that valuation date at time 3. So answer is those 3 deposits earning 10% a year, you would have $662 in the account on the day that third deposit of $200 is made at time 3, 3 years from now. And there's your calculator solution down there, nothing surprising there. Payment is minus 200. There's nothing in the account to start with, so present value is 0. We compute the future value and get 662. Now, this is when it changes a little. See where that arrow is now? With an annuity due when we have payments all along, if we put our calculator in begin mode, BGN, then it's going to give us the value on the date of the first deposit. Remember before, in end mode, we got the present value 1 period before the first deposit. So that's what you want to keep in mind on begin and end mode. So now we're asking the question, what's the present value of 3 $200 payments, each made at the beginning of the year instead of the end of the year with a 10% interest rate? So now the solution here, well, the present value of that first payment is $200. That's today. We take the present value of the second payment, present value of the third payment, add them all up, and we get a present value of this 3-period annuity as $547.11. And the calculator, put it in begin mode. N equals 3, 10%, payments are 200. We put it in as minus 200. 0 future value, and compute the present value at time 0 and get 547.11. So that's how your calculator works. Now what about the future value? Well, again, we've got beginning of year payments here, but when we ask the calculator what's the present value, put in N equals 3 because there's 3 payments, notice where that red arrow is. In begin mode, you get the future value 1 period after that third deposit is made, if that's the situation we're looking at. So now that first $200 earns interest for 3 years. The second earns interest for 2 years, and the third earns interest for 1 year as well, and that's this term right here. So in this case, our future value would be $728.20. And on the calculator, again, if we put it in begin mode, we've got 3 periods, 10%, $200 payments, present value is 0, and compute that future value of $728.20. So now we've taken the present value of a perpetuity, we've taken the present value of annuities, both regular annuities and annuities do, but that distinction you'll see is not as important as putting the problem out on a timeline and knowing where the value is that you're getting from the calculator, where it is if you're in begin mode, where it is if you're in end mode. And which one you use is just going to depend on the context, on the problem that you have, and the question that you're trying to answer. Now, our next learning outcome statement here says, well, what about if the cash flows are uneven? Well, that's not a problem for us because the way we've gone through it, we just need to take the future value of these three payments. Here we've got an account and we're depositing $300 one period from now, $600 two periods from now, $200 three periods from now. How much will be in the account at time 3 there? Well, the $300 earns 10% for 2 years, so we compound 10% for 2 years like that to get that time 3 value. Here is the time 3 value of the $600 deposit because that earns 10% for 1 year, so that's going to turn into $660. The $200 deposit is made right at time 3, so no interest accrues. We add them all up and get $1223. So here's what it looks like. We could do it with the calculator this way, taking the future value of each of those payments and adding them all up. So since our payments vary now, we can't just put in payment and end and use those regular time value of money keys before. But the only point here is if you need the future value of 3 payments, take the future value of each payment and add them all up. Same way with the present value of 3 payments. Just take the present value of each component and add them all up. So here's an example of that present value of uneven cash flows. And so here we're discounting this $200, the present values. Back here at time 0, we discount for 3 periods and then 2 periods and 1 period. Add them all up to get the time 0 or present value of those 3 uneven payments. Here it is on the calculator, but again, we're just taking the present value of each component and summing them. We can also do this with our cash flows functions, and you'll learn more about that as we go along. So let's take a look at some examples of using these. We've got a monthly payment on a $100,000 30-year home loan with a stated rate of 6%. Well, they're monthly payments, so we're going to need to divide that 6% by 12 months and get our effective monthly rate of 0.5%, 0.5%. And our present value, the amount we're borrowing, is $100,000. Our number of payments in 30 years, there's 360 monthly payments. Our future value is 0. That's because this is an amortizing loan. It's all paid off with the last house payment, the 30s, or last mortgage payment 360 in the last month of the 30-year period. So now we solve for the payment, and we get minus $599.55. So we've solved for the monthly payment that at that stated rate of 6% a year and monthly compounding, our level payments for 360 payments over 30 years, $599.55. And just as an additional bit here, we've got an example question. How much is the remaining principal, sometimes called the payoff amount? How much do you still owe just after you made your 85th payment? Well, that's about 7 years out. Well, this is just going to be a present value calculation. So just after the 85th payment is made, so here we are on the timeline, payment 86 is right here. So now we've got an annuity of payment 86 through 360, and the payoff amount on a loan that doesn't have any prepayment penalty is just going to be the present value of that, with the discounting going to be the stated interest rate in the loan. So now, n equals 360 minus 85. That's how many payments we have left, 275. So now set n to 275. Your calculator remembers the other stuff. Okay? It remembers the present value, it remembers that interest rate, and it knows the payment. And the future value is 0. So now we're just going to solve for the present value at end of the 85th month with 275 payments left. So now we're still in end mode, so that's fine. We compute the present value and say the outstanding balance after 85 monthly payments is $89,488. Here's a retirement savings problem that integrates some of these, and we're going to take a look at a timeline and how that helps you. When you're first doing these time value of money problems, you get into trouble or you're a little confused, or even if you aren't, it really makes sense to draw out that timeline. When are the payments in? What period are you looking for? What value are you looking for? So this problem, and it's a straightforward retirement problem, our client has $750,000 in savings and will retire 20 years from today. At that time, he needs 25 payments of $62,000 a year to begin. Now, luckily, this client knows exactly when he's going to die, which makes retirement planning much simpler. So the account's expected to earn 7% a year. So we're going to break this down into two pieces. First, we're going to take that retirement income that he needs and figure out how much money he has to accumulate when he makes that first retirement payment out of the account of $62,000. So we're going to figure out how much is needed at time 20 to fund retirement. Now, let's draw a little timeline here. And here we are at time 0, and here we are out here at time 20. So this is where the first $62,000 payment comes out. So what we're going to do, here's a little fancier version of my timeline. We've got those 25 payments of $62,000, first one at time 20. That's the day he retires. So that's actually, we're going to see the day the last deposit goes in as well. But we don't need to look at that yet. So we need $62,000 a year for 25 years, starting 20 years from today. So that's what we've got on our timeline. So when we calculate the present value of that, we're going to put it in begin mode, because remember, begin mode gives us a present value on the day of the first annuity payment. So put it in begin mode. Put in 25 payments of $62,000 each, 7% annual interest rate, compute the present value, $773,099. That's a negative number. That's how much we need to have in that account at time 20, if the return is 7%, to fund all 25 of those payments, to fund that annuity. So that's the first step here. Now let's look at the second step. Now we need to know, what annual deposit does she need to make? Oh, I guess it's a she. I kept saying he. What annual deposit does she make at the end of each year for 20 years to reach her goal? Well, here's our timeline now. Okay. We've got to find those payments. And that first payment we're going to make 1 year from now at time 1, and the last of those goes in at time 20. Now we know how much that has to grow to at time 20. It has to grow to $773,099 at time 20. So notice, that's our future value now. We've put it in as negative. The interest rate's 7, 20 payments, present value $75,000. Because remember, that's what we already have in the account at time 0. And then compute the payment and find out that the deposit to reach this $773,099 that we need to make each year, $11,778.68. So that's how we broke that down in two pieces. First, how much do we need at retirement? And secondly, okay, given how much we have now, how much do we have to save each period to reach that retirement goal? So that's one of the uses we have for this time value of money calculation technique. Now, remember, there's 5 things on that line, right? We've got N, we've got interest rate, the I over Y key, we've got present value, future value, and payment. So we can put in any 4 of these and solve for the 5th. So that's what we're looking at here. Elmer's won his $4 million state lottery. Good job, Elmer. and has been offered 20 annual payments of $200,000 each. That's how these lotteries often pay out, right? So that's your $4 million there. But they'll also offer you a single lump sum, and in this case, they've offered Elmer a lump sum of $2,267,000. So what's the annual discount rate used to calculate the lump sum payout amount? So now we're going to solve for I over Y. We know N, that's 20. We know the payment amount, that's $200,000. We know the present value. That's going to be $2,267,000, and then we can solve for the discount rate. So we're going to put it in begin mode because these lotteries, at least if you get the annual payments, you get the first one today. You don't have to wait a year for your first payment. So we're going to treat that as an annuity due. We want the $2,267,000 as a time zero value. That's what they would pay you like today instead of the annuity payments. So we put that in. Our payment is minus $200,000, and our present value, $2.267 million. Compute the interest rate and come up with 7%. And the last one we want to look at here is, well, we could also calculate the number of periods. So this is a little bit of a contrived example here, but it'll illustrate that. Elmer borrows $100,000 at 9%. That's our effective annual rate, and make annual end-of-year payments of $13,966. How many payments must Elmer make to pay off the loan? Well, again, we know 4 of these items, but we don't know the 5th. We know the future value is 0. We know the payment amount. We know the present value. And we know the interest rate. Now, remember, he's going to borrow $100,000. So that's why the present value is positive. That's money to Elmer. Those payments, those are money from Elmer. So they need to have a different sign, or your calculator will give you dreaded error message number 5, which in most cases mean straighten out your signs on the problem. So in this case, we put in those 4, we compute N, and figure out that 12 payments of $13,966 would just pay off that loan if the effective rate were 9% annually. So that's our introduction to the time value of money. Hope you find that helpful. We'll see you in the next segment.